A crimson streak cuts across the pre-dawn sky, invisible to the creatures roaming Earth below, yet carrying the power to reshape life itself. In the hours before impact, forests hum with the calls of dinosaurs, rivers flow under quiet sunlight, and oceans pulse with unseen rhythms. Then, in a single moment, the planet convulses as an asteroid collides, sending fire, ash, and shockwaves across continents. From trembling land to darkened seas, life faces its most sudden and catastrophic trial. Join us as we trace the 24 hours that changed everything, from calm to apocalypse. The silent approach, a vast void stretches between the distant stars, cold and unyielding, yet within it, a solitary mass hurtles toward an unknowing world. The asteroid, a hulking body 10 kilometers across, drifts at an astonishing velocity of nearly 20 kilometers per second, faster than any creature on Earth could conceive. Its surface, scarred by eons of cosmic collisions, glows faintly as micrometeoroids peel away fragments, releasing trails of vapor that shimmer like ghostly ribbons in the blackness of space. This enormous rock, invisible to all living eyes below, carries a kinetic energy estimated at 10 billion times that of the largest nuclear bomb ever detonated, a force capable of altering the course of life on Earth forever. Beneath this silent menace, life continues unaware. In the humid forests of the late Cretaceous, triceratops graze in small herds, their three-horned heads methodically tearing at fibrous cycads and conifers. These gentle giants leave footprints that, millions of years later, would serve as frozen evidence of their final routines. Along the edge of nearby rivers, Hadrosaurus probed the shallows with broad beaks, feeding on water plants, while tiny Cretaceous frogs leap between mossy stones, oblivious to the approaching catastrophe. Even in the skies, pteranodon glide effortlessly over the coastline, scanning the water for schools of fish, their elongated wings slicing through wind currents that have circulated unchanged for millennia. Within the oceans, life continues in measured patterns that would soon be upended. Mosasaurus, apex predators of the shallow seas, glide beneath waves that sparkle in the late Cretaceous sun. Schools of Xiphactinus, elongated predatory fish, dart in synchronized patterns, while ammonites spiral gracefully through water columns, feeding on smaller plankton and avoiding predators. The balance of predator and prey is precise, an intricate dance honed over millions of years, entirely unaware that it is about to be violently disrupted. The asteroid's approach, though invisible to these creatures, will instantaneously displace these relationships, reshaping marine ecosystems forever. Far above the Earth's surface, the atmosphere begins to whisper of the asteroid's impending intrusion, though not yet with detectable force. As the rock plunges toward the planet, it encounters the tenuous outer reaches of the atmosphere, where friction is minimal but rising. The air, at 80 kilometers above the surface, begins to compress, creating a faint heating effect that could someday be inferred from microscopic alterations in gas molecules trapped in ancient ice cores or sediment layers. Though imperceptible to the fauna below, these early interactions foreshadow the immense thermal and mechanical forces that will soon envelop the entire planet. On land, smaller mammals, such as early multituberculates and primitive marsupial relatives, scurry through underbrush, seeking insects, seeds, and shelter. Fossil evidence suggests these animals were largely nocturnal, emerging at dawn to forage, and their metabolic strategies allowed them to survive extreme temperature fluctuations. Yet no strategy could prepare them for an event of cosmic proportions, one that would challenge the very limits of survival. Even as the dinosaurs engage in daily routines, grazing, hunting, and nesting, the first minute signs of disaster are already mathematically certain. A collision course calculated across tens of millions of kilometers will culminate here in this fragile web of ecosystems. In the rivers and estuaries, the water reflects a sky unchanged by human perception, but subtly influenced by the asteroid's distant passage. Microscopic particles stripped from the asteroid's surface may already be entering Earth's upper atmosphere, though too rare to alter sunlight noticeably. These particles, analysed in modern sediment cores, contain trace metals and isotopes that allow scientists to reconstruct trajectories and estimate the asteroid's composition, predominantly carbonaceous, mixed with silicate minerals and nickel-iron deposits. The data suggest a density comparable to that of terrestrial rocks, yet the sheer velocity guarantees an energy release capable of vaporizing entire landscapes upon impact. Even at the poles, in regions where ice sheets stretch across the continents, life maintains its routines. Small theropod dinosaurs, adapted to cooler climates, forage for invertebrates and small vertebrates, leaving subtle trackways in frozen soil that will one day fossilize. Birds and bird-like theropods, predecessors of modern avians, flit between branches, their feathers catching the weak sunlight reflected from polar ice. Though thousands of kilometers from the impact site, these creatures are already fated to experience the secondary effects: shockwaves, atmospheric particles, and climatic disruption that will ripple outward with deadly precision. The asteroid's passage is not merely physical but a silent herald of cascading consequences. Even before contact, gravitational perturbations can slightly influence Earth's tides and minor atmospheric motions, though negligible to creatures below. Still, these changes remind us that the universe operates in a continuous chain of cause and effect. A single cosmic event can propagate in invisible ways, altering everything it touches. Fossilized sediments will later reveal tiny disruptions in coastal mudflats, a subtle testimony to the asteroid's approach, preserved across millions of years as a faint but immutable record of impending calamity. In these final hours, predators and prey alike exhibit no awareness of the approaching force. Tyrannosaurus rex, though formidable and highly sensory, scans its territory with keen vision and an acute sense of smell, tracking movements of smaller herbivores, yet remains blind to the vast rock descending from above. The intricate food webs, so carefully balanced over millions of years, continue uninterrupted, yet scientists today can trace sudden changes in fossil assemblages to this singular event. The patterns in growth rings, nesting behavior, and fossilized gut contents all bear silent testimony to a world unknowingly approaching its most cataclysmic hour. At the boundary between space and atmosphere, the asteroid maintains its silent, inevitable descent, carrying with it the potential to annihilate species, ignite global firestorms, and inject Earth's skies with dust and sulfuric aerosols. The distance is closing at unimaginable speed. In less than an hour, the first thermal and mechanical interactions with the planet will begin, transitioning the universe's quiet calculations into a violent display of physics made flesh. All the while, life persists in its daily rhythms: grazing, hunting, swimming, and nesting, completely unaware that the calm will give way to chaos in mere moments. In reflection, this vast juxtaposition of cosmic scale and fragile terrestrial life underscores the delicate balance of existence. The asteroid's silent approach reveals not just the vulnerability of individual creatures, but the interconnectedness of ecosystems that rely on constancy and predictability. As shadows lengthen and the day progresses toward its fateful end, a subtle tension permeates every forest, river, and ocean, hinting at the first intrusion of physical forces that will irrevocably reshape the planet. In these hours before contact, Earth remains deceptively serene, yet beneath the tranquil surface, the clock ticks inexorably toward a collision that will mark the boundary between the world that was and the world soon to be transformed. Whispers of heat and light, a shimmer appears at the edge of the atmosphere, unseen yet undeniable, as the asteroid begins to graze the outer layers of Earth's protective veil. At altitudes exceeding 80 kilometers, friction between the asteroid's surface and the tenuous air generates temperatures that climb into the thousands of degrees Celsius, producing a faint glow that stretches in invisible trails across the curvature of the planet. Microscopic particles ablate from the asteroid's crust, ionizing the surrounding air and forming luminous plasma streaks that race ahead of the main mass, leaving ephemeral markers in the high-altitude sky. Though imperceptible to the human eye, these first thermal interactions carry immense energy sufficient to perturb molecular bonds in nitrogen and oxygen, and initiate processes that will echo through the atmosphere and down to the surface below. Tiny sparks of ionized gas ripple outward, igniting streaks of light that momentarily illuminate the planet's surface. In the forests of Laramidia, Triceratops halt mid-step, ears swiveling and nostrils flaring, sensing changes in air pressure and subtle shifts in wind currents. Herding instinct compels these massive herbivores to huddle closer, their eyes scanning the sky for threats they cannot identify. Nearby, Hadrosaurus flicks its tail in nervous repetition, while juveniles nuzzle under the watchful gaze of adults, unaware that these cues originate not from a terrestrial predator, but from an invisible celestial intruder racing toward collision. Even pterosaurs, gliding effortlessly above rivers and lagoons, register the disturbances. Their wing membranes respond to the faint heating of the air, while their optic lobes perceive glints of light reflecting off distant clouds. Shadows lengthen beneath the forest canopy as smaller mammals, such as early multituberculates and primitive marsupial relatives, pause mid-forage. Their acute auditory senses detect vibrations imperceptible to larger creatures, while specialized olfactory receptors may sense subtle chemical shifts in the air caused by ionized particles descending from above. Fossil evidence of burrows suggests that these animals exhibited heightened nocturnal vigilance, and their freezing behavior at this moment demonstrates that even in the absence of visual confirmation, life begins to respond to the asteroid's approach. Across the plains, theropod dinosaurs, including juvenile Tyrannosaurus rex, halt in their hunting routines, noses elevated, nostrils flaring at disturbances invisible to all but their finely tuned senses. Waves in the shallow seas momentarily catch reflections of an alien light, invisible in origin but detectable through sudden temperature anomalies in surface waters. Mosasaurus shifts positions in mid-swim, muscular tails propelling them into deeper waters to avoid subtle heating, while schools of Shipphactinus dart erratically in response to minute changes in the surface tension of the water. Ammonites coil in defensive patterns, withdrawing tentacles as light streaks dance across the waves, an instinctive response preserved in the fossil record as a moment of sudden environmental stress. Even small aquatic insects and plankton show shifts in vertical migration, revealing that the asteroid's influence is simultaneously subtle and pervasive across ecosystems, both terrestrial and marine. Meteorological currents, if measured, would reveal early compression of air molecules and faint heating in the mesosphere. At 60 to 70 kilometers above the surface, friction-induced shockwaves begin forming minuscule pressure fronts, moving faster than sound, yet too weak initially to impact life directly. Nevertheless, these early ripples are detectable by organisms finely attuned to atmospheric perturbations. Fossilized pollen and spores from the KPG boundary, analyzed with modern microscopy, suggest minute dislocations in sediment patterns caused by these initial atmospheric shifts. Serving as a microscopic record of the asteroid's first touch upon Earth's protective envelope, the pterosaurs lift higher, wings catching light that has never been witnessed before, their large eyes, adapted for motion detection across vast distances, perceive streaks of illumination that are simultaneously dazzling and disorienting. Some glide toward the sun, instinctively moving with prevailing winds, while others hesitate, banking suddenly, as thermals shift unexpectedly in response to the asteroid's near-space passage. In these minutes, flight paths are subtly altered, predation opportunities disrupted, and territorial patterns temporarily suspended, evidence that even apex aerial predators are subject to the unseen influence of a celestial interloper. Even the smallest mammals freeze in mid-step, their forepaws grasping twigs or soil as if sensing the unseen. Early marsupialiformes, with delicate yet resilient skeletal structures, exhibit defensive postures, burrows unoccupied but ready for retreat. Insects, such as beetles and early ants, display erratic behavior, leaving minute trace fossils in sediment that would later reveal abrupt shifts in population activity. These tiny responses, while imperceptible in isolation, form a mosaic of life, reacting to the first tangible hints of impending catastrophe. A pattern scientists can reconstruct through paleontological evidence and modern analogues of animal stress physiology. A subtle warmth begins to trace the curvature of the planet, faint but inexorable, and thermal radiation penetrates the upper forest canopy, altering microclimates for brief moments. Diurnal plants may respond with instantaneous stomatal adjustments, while nocturnal fungi pause spore release, showing that the asteroid's influence reaches beyond visible life into ecosystems at the microscopic and chemical levels. Each ripple of heat, each photon scattering through air molecules, sets in motion a cascade of ecological and chemical responses that presage the larger shock that will arrive within minutes. Fossilized sediments of the KPG boundary hint at these first moments of atmospheric interaction. Trace metals, including iridium and nickel, deposited from the asteroid, mark the initial arrival of extraterrestrial matter in Earth's atmosphere. Tiny spherules formed from molten rock begin their descent into the oceans and land, invisible to life below. Yet their chemical signatures preserve a precise timestamp of the asteroid's initial atmospheric contact. This record allows modern scientists to reconstruct the sequence of events, confirming that the subtle flashes, thermal pulses, and ionization streams were not abstract phenomena, but measurable physical realities with immediate implications for global ecosystems. Across continents, the planet itself seems to hold its breath before the tremor arrives. Trapped in daily routines, animals sense disturbances without understanding their origin. Triceratops herds cluster defensively, Hadrosaurus juveniles pause mid-step, Mosasaurus glide to deeper waters, and flying pterosaurs adjust their thermals in near-perfect unison. This convergence of behavioral responses marks the first warning signs of destruction, hinting that the planet is about to tremble under forces no living creature could have anticipated. The atmosphere hums with energy, invisible yet inexorably approaching the Earth's surface, ready to translate celestial velocity into planetary catastrophe, and guiding all life toward the tremor that will soon redefine existence itself. The first tremor. The ground shudders beneath forests and plains, a pulse of energy travelling unseen yet undeniable, as the asteroid's collision translates its cosmic velocity into Earth's crust. seismic waves radiate outward at speeds exceeding 10 kilometers per second, propagating P waves first, followed by slower, more destructive S waves, creating a rolling ripple that will soon circle the globe. In this first instant, rocks fracture microscopically, loose sediment shifts imperceptibly, and the hidden prelude to devastation begins, detectable only by the most sensitive of life forms. Rivers ripple unnaturally as aquatic life senses the first vibrations, currents shifting in response to pressure waves transmitted through the water. Mosasaurus descend to deeper layers, muscles tensing as they sense a distant tremor, while schools of Cephactinus scatter, instinctively fleeing toward calmer depths. Ammonites retract their tentacles, adjusting buoyancy as minor pressure fluctuations make the normally stable water column briefly chaotic. Even microscopic plankton drift in erratic paths, evidence that the impact's force is already altering life beneath the waves. Massive herbivores halt abruptly, hooves sinking slightly into trembling soil as the vibrations reach their feet. Triceratops herds cluster in tight formations, heads low, ears swiveling to detect subtle differences in seismic frequency. Nearby, Hadrosaurus freeze mid-graze, tails flicking nervously, sensing a disturbance too vast to comprehend. Fossilized trackways preserved in sediment layers indicate abrupt stops and erratic movement, revealing that these animals experienced a moment of collective recognition that the earth itself had shifted beneath them. Tiny mammals scuttle into burrows, their keen senses detecting frequencies beyond human perception. Early marsupialiformes, weighing barely a kilogram, respond to P-wave vibrations that traverse meters of soil before the first S-wave hits. Burrows are tightened, body positions adjusted, and feeding temporarily abandoned as instinct overrides the search for nourishment. These survival strategies, honed over millions of years, momentarily protect some of the smallest creatures from the immediate chaos, highlighting how evolutionary adaptations can offer brief reprieves even in global catastrophes. Rock formations groan and fracture, amplifying the tremor through canyons and cliffs. Boulders shift, some tumbling into ravines, sending cascades of stone that trigger smaller, localized quakes. Fossil evidence of displaced stones and shattered sedimentary layers from the KPG boundary suggests that landslides were widespread within minutes of the impact. Across vast stretches of terrain, forests echo with cracking branches, the snapping of trunks, and the sudden collapse of undergrowth, converting seismic energy into an audible manifestation of catastrophe. Coastal waves rise and fall in irregular patterns, sending schools of fish and marine reptiles into sudden flight. The S-waves reach oceans within minutes, causing surface oscillations tens of meters high near the impact site and triggering the earliest tsunamis. Plesiosaurs dive rapidly to avoid turbulent surges, while coastal invertebrates such as crabs and mollusks are swept into temporary displacement zones. Geologic models estimate wave heights of up to 100 meters in the immediate impact vicinity, illustrating the staggering kinetic energy transferred from a single asteroid to global aquatic systems. Ammonites and plankton experience pressure changes that disrupt feeding and swimming rhythms, effectively pausing primary productivity in certain coastal areas. Plankton density fluctuations can be inferred from microfossil distributions and geochemical anomalies in sediment layers, demonstrating that even the smallest organisms are acutely affected by seismic and hydrodynamic disturbances. The cascading effect on the food web is immediate. Predators reliant on consistent prey patterns face confusion and dislocation, while herbivorous species on land and in shallow waters are indirectly impacted by shifts in nutrient cycles. Predatory theropods pause mid-chase, heads tilted toward the vibrations, instincts registering danger before sight confirms it. Tyrannosaurus rex, weighing over 7 tons, senses ground oscillations through bone-conducted vibrations in its skull and jaw, enabling rapid response to subtle shifts. Fossil trackways suggest sudden abandonment of hunting pursuits in response to tremors, indicating that apex predators were temporarily restrained by environmental signals rather than active threats. Smaller carnivorous species such as Dromaeosaurus demonstrate similar behavioral halts, retreating to elevated terrain or dense undergrowth in instinctive avoidance of collapse-prone areas. Forests echo with the cracking of branches and snapping of trees as energy courses through every root and trunk. The combination of seismic motion and unstable soils results in mass dislocations of vegetation, leaving habitats fragmented in mere minutes. Fossilized logs at the KPG boundary indicate horizontal displacement, charred tips, and broken trunks consistent with simultaneous thermal shock and mechanical force, offering tangible evidence of the asteroid's indirect effects before firestorms. These disruptions reshape microhabitats, creating unpredictable refuges and hazards for both small and large animals. From pole to pole, the Earth itself seems to pulse with the asteroid's presence, a vibration that connects the smallest burrowing mammals with towering dinosaurs through a shared, involuntary awareness of upheaval. Fossilized burrows, trackways, and marine sediment disruptions collectively illustrate the early moments of planetary-wide disturbance, capturing a synchronous response that unites ecosystems separated by distance, scale, and species. The tremor is both messenger and harbinger, signaling that the physical intrusion of the asteroid has begun and that landscapes, oceans, and life alike are about to confront forces beyond comprehension. Seen through the lens of deep time, these first tremors reveal the interconnectedness of life and planet, demonstrating that even before the asteroid's full impact, the Earth responds as a single organism to a cataclysmic stressor. Animals large and small, from the shallowest plankton to the apex predators of land and air, register the invisible energy coursing beneath their feet and fins. The vibrations, though imperceptible to most humans, carry a clear warning encoded in instinct, hinting that the next moments will bring not just tremors, but the full, violent consequences of collision, ushering in mass movements of creatures and landscapes that will redefine existence in ways unimaginable. Impact. Earth shattered. A deafening roar erupts as the asteroid collides, vaporizing mountains in a heartbeat, converting the kinetic energy of billions of tons of rock into a force beyond human comprehension. At the moment of impact, temperatures soar to tens of thousands of degrees Celsius, instantly melting and vaporizing the surrounding crust, forming a molten cavity hundreds of kilometers wide. Shockwaves radiate outward, compressing air and earth alike, producing a sonic boom that traverses continents in mere minutes. From the collision point, the Earth's surface becomes a theatre of chaos, where landscapes are obliterated before the eyes of any creature too close to survive. Molten rock explodes skyward, forming a towering plume of fire and debris that pierces the atmosphere. Spherules of molten material, some millimeters to centimeters across, are flung at hypersonic velocities, raining down across thousands of kilometers. Fossilized layers in the KPG boundary confirm that these droplets were deposited globally, marking the first minute of an impact that would alter ecosystems forever. The incandescent ejecta creates instantaneous firestorms in forests and grasslands, igniting vegetation and overwhelming herbivores and predators alike within the immediate radius. Shockwaves ripple across the landscape, toppling trees and fracturing the crust beneath massive herbivores. Triceratops and Hadrosaurus herds are thrown into chaos, massive bodies colliding as instinct cannot compensate for the instantaneous upheaval. Fossil trackways show abrupt terminations and overlapping footprints, evidence that life's intricate choreography is violently interrupted. Even the largest dinosaurs, despite their strength and size, cannot resist forces that rearrange entire habitats in minutes, leaving survival to chance and proximity to the epicenter. Rivers boil and surge as ejecta rains down, altering courses and drowning unsuspecting aquatic life. Mosasaurus and smaller fish are displaced from familiar hunting grounds, struggling against waves generated by rapid vaporization and atmospheric shock. Coastal ecosystems experience near instantaneous disruption, with tsunamis racing outward at supersonic speeds, inundating shorelines and sweeping marine and terrestrial organisms into chaotic, unpredictable patterns. The fossil record shows sediment slumping and abrupt faunal displacement consistent with these violent, waterborne pulses. The ground shatters beneath predator and prey alike, forcing an instantaneous pause in life's rhythm. Tyrannosaurus rex collapses into the seismic upheaval, jaws agape, while smaller carnivores are hurled from precarious perches or forced to abandon nests and kills. Insects, reptiles, and early mammals experience simultaneous decoupling from habitat structures, illustrating that impact energy is indiscriminate in its destructive reach. Even distant populations begin to feel the indirect consequences as atmospheric pressure waves prelude the next moments of global chaos. Flashes of incandescent heat sear the air, igniting forests and grasslands within kilometers of the impact. Pyroclastic firestorms sweep across the landscape, reducing forests to ash and creating lethal conditions for creatures caught beyond the immediate vaporization zone. The intense radiation and thermal pulse leave no escape for organisms within the radius, while those slightly farther experience burns, blindness, or severe stress. Geological evidence shows charred wood fragments, vitrified soil, and spheral deposits as markers of these extreme conditions. Gases trapped within fractured rocks explode outward, adding a chemical storm to the mechanical devastation. As the asteroid vaporizes and melts rock at the epicenter, volatile compounds, sulfur dioxide, carbon dioxide, and water vapor are suddenly released from deep strata. These gases combine with incandescent particles to form an immediate, localized acid rain potential and contribute to a sudden surge in atmospheric pressure. Measurements of KPG boundary layers suggest that these volcanic-style outgassing effects would have briefly superheated the air, producing toxic microenvironments that likely caused mass mortality in surviving land animals and disrupted nearby aquatic ecosystems. This chemical shock, invisible yet lethal, complements the mechanical destruction, highlighting that the impact's lethality was multidimensional, combining heat, force, and chemical stresses in a single catastrophic pulse. Fossilized spherules reveal the scale of molten droplets flung into the atmosphere, marking the precise moment of collision. These droplets carry traces of iridium and other extraterrestrial elements, offering modern science a timestamp of the event and proof of the asteroid's extraterrestrial origin. Their size, distribution, and chemical composition allow researchers to reconstruct trajectories, thermal effects, and even the impact angle, transforming ancient catastrophes into measurable, understandable phenomena. These particles are silent witnesses to a moment that annihilated life locally, while setting the stage for global consequences. Even the largest dinosaurs, from Tyrannosaurus rex to Triceratops, are subjected to forces that their mass and strength cannot resist. Fossil evidence of fractured bones, overturned skeletons, and abrupt cessation of trackways demonstrates that survival in the immediate radius is virtually impossible. Smaller creatures, however, may find refuge in burrows, water bodies, or distant regions, illustrating the uneven reach of the impact's devastation and hinting at the selective pressures that would shape post-impact ecosystems. The oceans convulse under the impact, sending tsunamis outward at supersonic speeds. Coastal and shallow water ecosystems are instantly destabilized. Marine reptiles and fish are forced to abandon feeding zones or risk death, while suspended sediments record massive turbulence. Geophysical models suggest waves hundreds of meters high near the impact site, gradually dispersing globally but leaving catastrophic surges along distant coastlines. Even subtle pressure and thermal changes in the water column ripple outward, affecting plankton and other microscopic life, demonstrating that the asteroid's reach extends from the largest apex predator to the tiniest organism. From the epicenter, Earth seems to breathe molten fury, a violent exhalation that will echo across the globe. Landscapes, forests, and oceans alike bear the scars of instantaneous destruction, and life is forced into chaos without warning or mercy. Yet, even amid this overwhelming devastation, subtle signs suggest that some distant ecosystems will survive, insulated by geography or sheer fortune, providing the faintest glimmer of continuity in a world suddenly transformed. These immediate events, violent and spectacular, herald a new chapter in Earth's history, where molten rock, shockwaves, and atmospheric upheaval combine to define the boundary between the age of dinosaurs and the survival of life beyond the impact. Fire from the sky. Red-hot droplets pierce the sky, raining incandescent doom upon forests and plains, their molten paths igniting foliage the moment they touch. Each spheral carries the kinetic memory of the asteroid, delivering concentrated heat capable of igniting wood, leaves, and grasses instantly. Within minutes, localized fires merge into unstoppable fronts, consuming everything in their path. Fossil evidence of widespread charcoal and burned plant material in KPG boundary layers confirms that these firestorms were not isolated, but a planetary-scale phenomenon reaching continents far from the impact site. The first sparks ignite dry foliage, igniting flames that race faster than any terrestrial predator. Hadrosaurus herds stampede, their coordinated flight disrupted by flames that leap across the ground, consuming underbrush and destabilizing terrain. Even the cleverest predators, including dromaeosaurids, are forced to abandon hunting strategies, redirecting instinct towards survival. Fossilized trackways reveal abrupt diversions and chaotic patterns consistent with animals fleeing rapidly advancing fire fronts. Smoke rises in thick plumes, obscuring the sun and dimming the world beneath. The sudden reduction in sunlight begins cooling surfaces, even as the fires continue to radiate intense heat. Atmospheric particulates, enriched with carbon and silicate from vaporized rock and vegetation, begin forming a global veil of smoke, laying the foundation for the prolonged darkness and climatic disruption that will follow. Birds and flying reptiles, including pterosaurs, are caught in this smoky labyrinth, struggling to navigate turbulent, heated air currents. Massive herbivores stampede through fire-scattered undergrowth, leaving trails of panic and destruction. Triceratops herd behavior is both a survival strategy and a vulnerability, as groups collide, stumble into flames, or become trapped by fallen trees. Their thick hides provide minimal protection against radiant heat, forcing rapid movement toward water or less dense vegetation. Smaller mammals, though more agile, face suffocating smoke and scorching temperatures that test the limits of their burrows' protective qualities. Birds take flight, wings silhouetted against a crimson horizon, driven by instinct rather than sight. Enantiornithines and early avians ascend into thermals, seeking refuge in higher altitudes, while winged insects are caught in turbulence, their small bodies vulnerable to extreme temperatures. Evidence from fossilized wing imprints suggests chaotic dispersal patterns, indicating that aerial escape was perilous, with survival dependent on both skill and fortune. Coastal reeds and mangroves are consumed in seconds, leaving ash-strewn shorelines in their wake. Mosasaurus and other marine reptiles, though initially insulated from terrestrial flames, experience indirect consequences as sediment-laden runoff and ash alter salinity and oxygen levels near shore. Coastal ecosystems are reshaped, combining fire-induced destruction with chemical and physical disturbances, demonstrating that the asteroid's effects reach beyond immediate landfall into the seas. Thermal radiation from re-entering ejecta reaches hundreds of kilometers, igniting regions far from the initial impact. The immense energy transfer produces a simultaneous ignition over vast swaths of land, creating overlapping firestorms that eventually coalesce into a global conflagration. Fossilized charcoal layers, along with microscopic spherules preserved in sediments, provide tangible evidence that firestorms were widespread and catastrophic, confirming the scale of devastation suggested by modeling and impact simulations. Gases rising from burning forests generate violent atmospheric turbulence, creating gusts and unpredictable microclimates that further imperil life. Hot updrafts, downdrafts, and rotating columns of fire-driven air push animals off course, scatter flocks, and intensify flame spread. This chaotic interaction between fire and atmosphere amplifies destruction in ways that are difficult to predict, even for species with evolved escape behaviors. Fossilized pollen deposits and sediment layers indicate sudden redeposition caused by wind-blown ash and soil, evidence of these firestorm-driven microclimates. Fossil charcoal deposits in KPG boundary layers confirm the breadth and intensity of these ancient conflagrations. Chemical analysis reveals elevated carbon and polycyclic aromatic hydrocarbons, consistent with high-temperature combustion of plant matter. This evidence demonstrates that firestorms contributed significantly to immediate mortality and habitat destruction, making them a primary driver of ecological collapse in the hours following the impact. Soils stripped of vegetation and subjected to extreme heat are sterilized in many regions, reducing plant regrowth and triggering cascading ecological effects. Herbivorous dinosaurs and mammals suddenly find food scarce, while predators face scarcity compounded by the loss of prey. This rapid ecosystem destabilization extends the mortality zone far beyond the flames themselves, illustrating that the fire's effects are both direct and indirect, reshaping life in subtle yet devastating ways over the following days. Even burrowing mammals and reptiles face suffocating heat and smoke, testing the limits of their evolutionary refuges. Burrows that had provided temporary protection from seismic shock now become lethal ovens as smoke infiltrates subterranean spaces. Fossilized burrow casts, coupled with evidence of sudden mortality, show that even small-scale shelters could not fully mitigate the combined effects of radiant heat, chemical gases, and airborne particulates, highlighting the asteroid's all-encompassing reach. Re-entering ejecta ignites distant regions hundreds of kilometers from the impact, creating isolated fires that link into a network of global destruction. Evidence of charred plant deposits and ash layers in regions far from the Chicxulub site suggests that even remote habitats were not immune, extending the ecological catastrophe to species that initially avoided direct impact zones. These far-reaching ignitions contribute to the growing atmospheric opacity and set the stage for the prolonged global darkness to come. Amid the haze of fire and ruin, a global atmosphere thick with smoke and particulate matter begins to emerge, foreshadowing a planet veiled in darkness. Flames illuminate a world simultaneously collapsing and transforming, while the first hints of ash-induced cooling and reduced photosynthesis signal that survival will depend on resilience beyond immediate escape. In these infernos, life is both tested and extinguished, preparing the stage for the coming months when darkness and climate disruption will dictate which species persist and which vanish from Earth forever. A poisoned breath, a fine veil of soot dims the sun, casting a shadow over once lush landscapes, turning vibrant forests and plains into a grey, oppressive world. The thickened atmosphere reduces visible light, causing temperatures to drop in exposed regions, while leaving lingering heat near smouldering fire zones. Fossilized plant material shows evidence of sudden chlorophyll loss and stress, confirming that photosynthesis was immediately disrupted, threatening herbivores that depended on leaves, shoots, and fruits. Sulfur-laden aerosols mingle with smoke, creating an acidic haze that corrodes both leaf and lung. Triceratops and Hadrosaurus inhale the tainted air, showing evidence of stress in fossilized bone microstructure and tooth enamel, suggesting rapid physiological strain. Birds, including pterosaurs and early avians, struggle against thickened air, wing beats failing to lift them fully, forcing them to land amid toxic fogs. Even the smallest mammals are challenged, their burrows fill with smoke, compromising the microclimate they relied on for safety. Airborne particles settle on water, disrupting aquatic life and altering oxygen levels. Rivers, ponds, and coastal pools receive a sudden influx of ash and chemical aerosols, producing lethal conditions for fish and amphibians. Fossilized sediment layers show abrupt die-offs in freshwater ecosystems, while trace elements indicate shifts in water chemistry consistent with high particulate and sulfur content. The cascading effects ripple outward, demonstrating that even organisms distant from flames are not spared. Flying creatures descend in confusion, wings beating against thick, choking air currents. Enantiornithines and insectivorous birds falter in flight paths, crashing into trees or dropping into rivers in a desperate search for breathable air. Modern models suggest that aerosol density reached levels sufficient to reduce oxygen availability by several %, enough to induce hypoxia in mid-sized vertebrates. The fossil record hints at abrupt mortality, visible in flattened or contorted skeletons in ash-rich deposits. Herbivores hesitate at charred clearings, sensing a change in the quality of the air itself. Ankylosaurs and smaller mammals stop feeding, nostrils flaring as they attempt to detect safer zones. Behavioral paralysis, combined with limited mobility in some species, compounds mortality risk. Fossilized dung layers show abrupt cessation, supporting the notion that many plant eaters succumb to respiratory distress or the indirect effects of food scarcity within hours. Microscopic ash infiltrates burrows and nests, penetrating even the deepest refuges of small mammals and reptiles. Cimolodontidae and multituberculates, typically insulated from surface hazards, experience lethal exposure to toxic particulates. Sediment infillings of burrows show concentrated ash deposition, confirming that subterranean shelters could not fully protect life from the pervasive atmospheric contamination. These deposits reveal that the air itself became a predator, invisible yet deadly. Fossil evidence shows stress markers in bones and teeth, indicating starvation and respiratory distress within days. Histological analysis highlights accelerated bone growth interruptions and enamel hypoplasia, suggesting that even survivors of initial firestorms and impact trauma were physiologically taxed. Predators, deprived of healthy prey, struggle to meet energetic demands, and entire food chains begin to collapse. These subtle but measurable biological indicators offer a window into the immediate toll of poisoned air on terrestrial ecosystems. The interplay of smoke, ash, and chemical aerosols begins altering weather patterns, hinting at the climatic catastrophe yet to come. Reduced sunlight triggers surface cooling, while suspended particulates influence precipitation, creating acid rain and erratic storms. Fossil pollen records show sudden diebacks in plant communities, consistent with rapid climatic stress, while sediment cores confirm that atmospheric opacity persisted for weeks to months. Life now faces a dual threat: toxic air and the early onset of post-impact winter. Global sunlight reduction drastically diminishes photosynthesis, forcing herbivores into desperate foraging attempts. Early estimates suggest that nearly all photosynthetic plants were under stress within hours, evidenced by leaf cell collapse and fossilized cuticle damage. Herbivorous dinosaurs, reptiles, and mammals encounter increasingly barren clearings, while secondary consumers struggle as their prey disappears. This cascading plant-animal disruption underscores the interconnected vulnerability of ecosystems even beyond the immediate fire zones. Long-term respiratory and physiological stress emerges as animals inhale ash-laden air for hours. Fossilized vertebrae show microfractures and abnormal growth patterns in some mammals, suggesting energy diversion towards survival in low oxygen conditions. Dinosaurs exhibit similar signs in bone microstructure, indicating systemic stress, while isotopic analysis of teeth and bones reveals shifts in metabolism and diet. This silent, invisible toll amplifies the mortality initiated by fire and heat, confirming that the asteroid's effects extend far beyond immediate destruction. Behavioral disruptions become widespread as creatures attempt to navigate a dimmed, poisonous world. Birds drop prematurely to the ground, some entering rivers or shallow lakes to escape the thickening haze. Large herbivores pause or retreat into valleys, unaware that acidified fog and particulate deposition follow them into refuges. Predators, unable to locate prey, abandon territories or attack one another, intensifying ecosystem instability. Fossil assemblages suggest abrupt migrations and local population collapses, demonstrating that survival now depends on acute adaptability to invisible atmospheric hazards. Predators find prey scarce, both from fire-related deaths and the sudden exhaustion of their own energy reserves. Tyrannosaurus rex, though once apex, faces empty hunting grounds and weakened prey, forcing desperate scavenging and increased intraspecific conflict. Smaller carnivores, such as dromaeosaurids, likewise confront food scarcity compounded by respiratory stress, highlighting that survival pressures are now chemical as well as physical. Fossil assemblages suggest abrupt population bottlenecks in carnivorous species immediately following the firestorms. Surviving against the suffocating air, life clings tenuously, a fragile echo of the thriving ecosystems that existed only hours before. Trees stand blackened and leafless, rivers carry suspended ash, and the sky remains a perpetual grey curtain. Even creatures that survived fire and seismic shocks now struggle with every breath, foreshadowing the mass extinctions to come. In this choked, dimmed world, life is forced to endure its first sustained challenge from the asteroid's aftermath, a silent and invisible killer that sets the stage for the ecological upheaval of the following days and months. The last calls. A sudden hush falls over the scorched forests, broken only by faint, desperate movements. Animals that survived the initial fires and poisonous air now face the cumulative strain of heat, smoke, and ash. Fossilized plant and bone evidence indicate that herbivorous dinosaurs such as Hadrosaurus and Triceratops were rapidly succumbing to starvation and respiratory stress, unable to forage effectively under dimmed sunlight and toxic haze. Even large mammals, like multituberculates, show signs of abrupt physiological strain, demonstrating that no species, regardless of size, could entirely evade the asteroid's immediate reach. Oceans shimmer with a deadly sheen as countless fish and invertebrates falter in oxygen-starved waters. Marine reptiles, including mosasaurs and smaller aquatic reptiles, struggle in coastal zones, where heat from re-entering ejecta and chemical alterations raise water temperatures sharply. Sediment layers from the KPG boundary reveal sudden mass mortality, with fossilized schools of fish preserved in positions indicating collapse and hypoxia. Tiny plankton and ammonites also vanish from the record, highlighting that both micro and macro-scale marine ecosystems were simultaneously imperiled. Vast herds of herbivorous dinosaurs stumble and collapse, their weakened bodies unable to escape the poisoned environment. Trackways preserved in ash and mud demonstrate abrupt halts and chaotic movements, capturing a snapshot of panic and disorientation. Fossilized dung layers abruptly stop, indicating that digestion and feeding ceased under extreme environmental stress. Predators, including Tyrannosaurus rex and smaller theropods, encounter an emptying food chain, their hunting grounds littered with weakened or dead prey, forcing desperate scavenging and heightened intraspecific conflict. Silent predators roam abandoned hunting grounds, sensing that the world they knew has vanished. Skeletal evidence suggests predatory dinosaurs and mammals struggled with oxygen deprivation, fatigue, and scarcity of prey. Behavioral responses inferred from fossil trackways and nesting areas indicate erratic movement, territory abandonment, and competition that intensified mortality risk. Even apex predators are vulnerable. Their survival is dependent on the few remaining herbivores capable of movement, underscoring the fragility of life chains immediately after the impact. Impressions in mud and ash show abrupt halts, erratic turns, and frantic attempts to flee. Dinosaurs of multiple species, small mammals, and birds exhibit movement patterns suggesting confusion, panic, and sensory overload. Fossilized footprints in North American and Mexican strata demonstrate that entire herds changed direction suddenly, likely responding to smoke plumes, seismic tremors, or the stress of toxic air. Nesting sites indicate sudden abandonment, with eggs preserved unhatched, frozen in the moment of catastrophic environmental change. In the fading light, gliding and flying creatures falter, some never returning to the trees they called home. Pterosaurs and early birds experience acute respiratory stress, compounded by visibility reduction from dense aerosols. Wing structure and body mass analysis indicate that many could not sustain flight, leading to groundfall in dangerous environments. Sedimentary deposits capture these events as articulated skeletons in lifelike poses, frozen mid-struggle, emphasizing the immediacy of mortality and the widespread reach of the impact's lethal effects. Marine reptiles thrash in turbulent coastal waters, struggling to breathe in waters heated by ejecta and shockwaves. Mosasaurus, plesiosaurs, and small bony fish confront abrupt temperature spikes, reduced oxygen, and altered salinity levels. Isotopic studies of KPG boundary fossils show rapid shifts in water chemistry, confirming that heat and chemical toxicity combine to devastate marine life alongside terrestrial collapses. Fossilized remains in shallow coastal sediments suggest simultaneous die-offs, indicating that no refuge was entirely safe in the hours following impact. Layers of sediment accumulate remains with a suddenness that speaks to catastrophic, nearly simultaneous deaths. Charcoal and ash mixed with soil preserve evidence of fires, toxic aerosols, and immediate burial of animals in a snapshot of global mortality. Analysis of these layers shows differential preservation, with herbivores, carnivores, small mammals, and marine organisms all represented, revealing the indiscriminate nature of this early extinction pulse. Plants, too, are affected. Pollen and leaf cuticle fossils indicate sudden photosynthetic collapse. Hidden burrows and nests reveal the quiet fate of small mammals and reptiles, whose shelters offer little defense. Multituberculates, small lizards, and hatchling reptiles succumb to smoke infiltration, acidified water, and disrupted microclimates. Nest structures containing eggs show abrupt cessation of development, corroborated by shell damage and embryonic fossil analysis. These small, often overlooked species demonstrate that even protected habitats were not immune to the invisible and lethal after-effects of the asteroid. Groups of animals attempt to migrate toward presumed safety, only to encounter barriers in the form of fires, fallen trees, or toxic air. Fossilized trackways suggest abrupt directional changes and erratic movements consistent with panic behavior. Evidence indicates that ankylosaurs and smaller herbivores tried to cluster together for protection, yet the rapid environmental deterioration prevented effective group defense. Predators took advantage of these gatherings, further accelerating mortality, creating a cascading pattern of deaths across species. Cloaked in the ruin of a forest laid to flame, beneath the charred canopies and scorched soils, the smallest creatures also meet their end in silence. Microbial mats, insects, and soil-dwelling arthropods collapse under heat, chemical toxicity, and sudden habitat loss. Fossilized amber and sediment records suggest that entire insect populations, including beetles, cockroaches, and termites, vanished in localized regions. While microbial communities responsible for nutrient cycling were abruptly disrupted, the sudden die-off of decomposers accelerates the breakdown of organic matter, further destabilizing terrestrial ecosystems. Even microscopic spores and pollen grains reveal heat-induced deformation, evidence that the biosphere's smallest constituents are not spared in the initial hours of the catastrophe, underscoring the universality of mortality from the largest dinosaurs to the tiniest soil organisms. As extinction grips the planet, from the first signs of universal mortality emerges a chilling awareness. The fragile balance of life is shattering. Across continents and oceans, both visible and microscopic ecosystems unravel in hours, leaving an ecological vacuum in which survival depends on immediate adaptability and sheer chance. The first wave of deaths sets the stage for the full-scale mass extinctions that will reshape life on Earth, reminding us that the asteroid's legacy is not only in the impact itself, but in the cascading, relentless chain of consequences that follows, marking the planet's ecosystems for permanent transformation. The tsunami awakens. Mountains of water surge suddenly, racing across ancient shorelines and river deltas. The asteroid's impact displaced unimaginable volumes of ocean, generating waves that tore through coastal forests and inundated river valleys. Fossilized sediment layers reveal chaotic bedding and rip-up clasts, indicating waves hundreds of meters high in local areas, traveling at speeds capable of sweeping away creatures both small and enormous. Shoreline ecosystems, where dinosaurs nested and marine reptiles hunted, are instantly overwhelmed, leaving behind a jumbled record of life caught in motion. Marine reptiles are swept from coastal reefs into turbulent currents, struggling against the relentless force. Mosasaurus and plesiosaurs, normally dominant apex predators, are tossed into unfamiliar waters, while smaller fish collide with debris and each other in frantic attempts to escape. Sediment cores show densely packed remains, sometimes preserving articulated skeletons entangled with shells and plant matter, capturing a sudden and violent moment in the fossil record. The physics of water movement demonstrates that even the strongest swimmers had little chance of survival near the impact site. Ammonites, plankton, and schooling fish collide with debris, leaving traces now preserved in tsunami-laid sediments. Tiny shells, crabs, and shrimp exoskeletons are deposited alongside crushed vegetation, mud, and larger vertebrate remains, creating a catastrophic melange. This sudden mixing of marine and terrestrial life provides paleontologists with some of the clearest evidence of the immediate ecological havoc wrought by the asteroid. Oxygen-depleted waters in coastal zones compounded mortality, leaving even surviving deep-water species struggling to recover. Shore-dwelling dinosaurs and small mammals are caught unprepared, their nesting grounds inundated in moments. Fossil trackways abruptly terminate in fine layers of sand and mud, preserving the last frantic movements of hadrosaurs, ceratopsians, and early mammals. Nest sites are buried under sediment, with eggs crushed or preserved in situ, a testament to the speed and indiscriminate power of the waves. Even animals that could climb or burrow faced barriers. Uprooted trees, displaced boulders, and sudden debris flows created deadly traps along every flooded path. Uprooted ferns, shrubs, and mangrove-like trees are carried inland, their roots ripped from the soil and deposited in chaotic mounds. These once stable habitats, rich with shelter and food, vanish within minutes, leaving terrestrial survivors with no refuge. Fossilized plant debris, alongside vertebrate remains, demonstrates that destruction is universal. Both flora and fauna are swept into the same sedimentary layers. This obliteration of coastal vegetation compounds the immediate starvation and stress already affecting surviving animals. Rip-up clasts and chaotic sediment layers record the unparalleled kinetic energy released into shallow marine environments. Wave height, velocity, and inland penetration can be inferred from these deposits, indicating that in some regions water travelled tens of kilometres inland, stripping topsoil and vegetation. Fossilized logs, shells, and vertebrate remains mark a chaotic interface between marine and terrestrial ecosystems, capturing the violence of the first hours after the impact. Even modern analogues, such as the 2004 Indian Ocean tsunami, pale in comparison to the scale and energy recorded here. Currents carve new channels, depositing overturned logs, fossilized carcasses, and fragmented shells across vast tracts of land. Sedimentological studies suggest repeated surges as waves reflected off continental shelves and river mouths, creating secondary currents that compounded destruction. Fossil assemblages in these deposits often contain a mixture of species from different habitats, showing that terrestrial and marine ecosystems collided in catastrophe. Even plankton and microinvertebrates preserved in the sediments show the scope of the upheaval. Tidal surges ripple inland, erasing trackways and evidence of animal movement from the past hours. Predator-prey interactions abruptly cease, leaving evidence of abandoned carcasses, empty nests, and scattered remains. Evidence of herding behavior, migration attempts, and last-minute escapes is abruptly cut short in the sedimentary record. Small mammals and lizards, which may have survived fires or suffocating air in earlier hours, are buried under meters of sediment, indicating that even previously safe refuges offered no sanctuary. Fossil beds reveal mixed assemblages of marine and terrestrial species, frozen together in catastrophic deposition. Large reptiles, dinosaurs, and small fish share the same layers, offering a vivid illustration of the indiscriminate nature of tsunami mortality. Isotopic analysis of shells and bone fragments confirms rapid burial and limited decay, preserving a snapshot of the disaster in geological time. This mingling of ecosystems in death starkly contrasts the separation seen in life, underscoring the chaos unleashed by the impact. In the aftermath, shallow lagoons, estuaries, and river mouths lie barren, stripped of life, or buried under meters of sediment. Survivors face a dramatically altered landscape where topography, vegetation, and prey availability have been violently reshaped. Coastal forests, marshes, and mangrove-like habitats that once supported diverse assemblages are now gone, creating ecological voids that will persist for decades. Geological evidence hints at multiple wave pulses, suggesting a repeated battering that further hindered the ability of animals to escape or recover. Small refuges remain. Deep-water marine zones, highlands, and inland river bends harbour the few surviving organisms. These pockets of life, often hidden from immediate destruction, foreshadow the next stages of survival, where the climate, atmospheric opacity, and rising heat will dictate who endures. Fossil evidence from later strata suggests that only creatures able to adapt to radically transformed habitats or find temporary shelter will persist beyond these first hours of planetary-scale chaos. The power of water fades, leaving behind a landscape irrevocably transformed, yet signalling that survival will now hinge on adaptation to the changed skies and warming Earth. While tsunamis have claimed countless lives in hours, the survivors, whether in deep oceans, inland refuges, or higher elevations, now confront the next phase of catastrophe: scorching heat, firestorms, atmospheric opacity, and poisoned air. These initial deluges are only the first chapter in a sequence of planetary-scale disruptions that will decide which species endure and which vanish forever. Dark oceans, silent depths, a veil of darkness descends over the open ocean, muting the rhythmic pulse of waves. Dust and soot from the asteroid impact obscure sunlight, cutting off the photosynthetic energy that plankton rely on. Coccolithophores and foraminifera, tiny but critical primary producers, begin to collapse within hours, and the ripple effects cascade through the food web. Fossil evidence shows abrupt reductions in microfossil abundance immediately following the impact, underscoring how even the smallest organisms were not spared from the environmental shock. Rising temperatures ripple through shallow shelves, forcing marine reptiles and fish into frantic movement. Shallow water zones warm rapidly from the heat of ejecta re-entry and atmospheric firestorms, driving mosasaurs, plesiosaurs, and schooling fish toward deeper, cooler waters. Many animals, adapted for relatively stable temperatures, encounter physiological stress, reduced hunting efficiency, and increased mortality. Oxygen solubility decreases in warmer waters, further compounding physiological strain for all aquatic life. Paleothermometry from sediment proxies suggests local temperature spikes of 5–10 degrees Celsius in the first hours, enough to push sensitive species beyond survivable thresholds. Microscopic plankton falter as sunlight dwindles and waters grow increasingly acidic. Sulfuric aerosols from vaporized rocks dissolve into seawater, lowering pH levels and threatening the shells of mollusks, crustaceans, and plankton. Coccolithophore skeletons, made of calcium carbonate, begin to dissolve, removing a key component of marine sediment and destabilizing coastal food webs. Stable isotope analysis of marine sediments indicates abrupt acidification events consistent with rapid post-impact chemical shifts. These environmental stressors eliminate the reproductive capacity of small invertebrates, setting the stage for cascading starvation in higher trophic levels. Small crustaceans, ammonites, and benthic mollusks drift helplessly, their survival contingent on fleeting oxygen pockets. Fossil assemblages from coastal basins show dense clusters of these organisms preserved in anoxic sediments, trapped in sudden environmental collapse. Modern analogues, such as hypoxic zones in estuaries, demonstrate how quickly small invertebrates can die when oxygen levels fall below critical thresholds, often within hours. Their rapid disappearance ripples upward, leaving predators with nothing to hunt and reducing biodiversity at every layer of the ecosystem. Sudden acidification triggers an invisible storm, eroding the calcium carbonate shells of ammonites and nautiloids. The rapid drop in pH dissolves protective exoskeletons before these creatures can complete reproductive cycles, effectively halting populations in mid-generation. Fossil evidence from impacted marine strata shows fragmented shell layers and abrupt population declines in these taxa, highlighting a vulnerability previously underappreciated. Juvenile cephalopods, unable to cope with the chemical stress, die in vast numbers, removing a critical link in predator-prey networks. These subtle chemical assaults, invisible to the eye, quietly undermine ecosystem resilience even as larger, more dramatic catastrophes unfold. Reef ecosystems crumble silently, leaving intricate structures reduced to skeletal remnants. Coralline algae and reef-building organisms succumb to heat, acidification, and sedimentation, leaving behind skeletal frameworks devoid of life. Fossil reef layers show evidence of rapid deposition of ash and silt, preserving collapsed structures that mark one of the most abrupt habitat losses in Earth history. With reefs gone, fish, cephalopods, and other shelter-dependent species face exposure and predation in an increasingly hostile environment. Large predatory fish and mosasaurs navigate a world suddenly stripped of prey, instincts overridden by scarcity. Fossil evidence from rapid death assemblages shows adult mosasaurs and large teleosts co-located with exhausted, dying prey species, illustrating the collapse of predator-prey dynamics. Behavioral adaptations, such as hunting in deeper waters or expanding territory, are no longer sufficient as the foundational food web disintegrates. Even apex predators that survived the initial waves of destruction confront imminent starvation. Sinking organic material provides temporary sustenance, but cannot offset the collapse of primary food sources. Detrital rain from dead plankton, crustaceans, and fish creates brief feeding opportunities for scavengers, from deep-water amphipods to smaller reptiles. These ephemeral resource surges, however, cannot sustain populations over the coming weeks and months. Geochemical proxies in sediment cores reveal concentrated organic layers, highlighting both the temporary abundance and its fleeting nature. Deep-sea environments, once stable refuges, now experience subtle thermal shifts and oxygen depletion that ripple through the food chain. Even below 200 meters, temperature fluctuations and anoxic pockets affect benthic organisms such as crinoids, echinoids, and bottom-dwelling fish. Fossil evidence indicates shifts in species composition and abundance in deep-sea sediments, suggesting that no habitat remained completely insulated from the asteroid's global consequences. Currents and upwelling patterns falter, stranding nutrients and trapping waste in isolated ocean pockets. With the sudden disruption of global circulation, nutrient flows that sustain deep-sea communities are interrupted, leaving some regions with starvation, while others accumulate decomposing matter. Fossilized detritus layers indicate oxygen-starved zones where benthic invertebrates and small fish suffocated en masse, creating unique mass mortality horizons in the sedimentary record. Even large predators that ventured into these pockets encounter inhospitable conditions, demonstrating that survival in the deep sea is contingent not only on temperature and oxygen, but also on dynamic nutrient availability. This hidden choreography of currents and chemistry underscores how complex and interconnected marine ecosystems truly were, and how quickly they unraveled. Shifting light levels and opaque waters disrupt diurnal behaviors in fish, cephalopods, and marine reptiles. Many species rely on visual cues for hunting, mating, and schooling, and the loss of light exacerbates their vulnerability. Fossil evidence of schooling fish and cephalopod burrows indicates sudden behavioral collapse, coinciding with light attenuation, showing that darkness itself becomes a lethal environmental stressor. Sedimentary layers record abrupt chemical changes, marking one of the fastest marine disruptions in Earth's history. Sulfur isotopes indicate acidification pulses, while carbon isotopes reveal a sudden collapse in primary productivity. Microfossils and shell fragments embedded in these layers offer an unprecedented view of extinction processes unfolding in near real time. The geological record confirms that the oceans, vast and previously stable, were rendered hostile within hours to days. As light fades, waters acidify, and oxygen levels drop, life clings to refuges while the planet above continues to burn and suffocate, hinting at the dual onslaught awaiting terrestrial ecosystems. Some plankton persist in deep photic zones or in gyres sheltered from immediate heat, while scattered predators survive in cooler, oxygen-rich pockets. These fragile refuges offer a glimpse of resilience, but the cascading failures of food webs and habitat destruction foreshadow further waves of mortality. The oceans, though vast, are now quieted, a silent mirror to the fire, ash, and poisoned air that will soon devastate the land. Ignition of the planet. Flames erupt across the horizon, consuming treetops and grasslands in seconds. The re-entering asteroid ejector strikes dry vegetation, igniting wildfires that race ahead of any wind-driven advance, leaving a charred and acrid landscape in their wake. Fossil charcoal deposits from the KPG boundary indicate that forests and coastal plains were set ablaze within hours, illustrating the sheer velocity of this ignition. Smoke rises in thick, choking columns, carrying heat and particulate matter far from the initial impact zones. Ash rains down like a fine grey snow, coating every branch, leaf, and creature. Tiny particles infiltrate the lungs of land-dwelling reptiles, mammals, and birds, causing respiratory distress. Paleontologists note soot layers within sedimentary deposits that coincide with mass mortality horizons, providing direct evidence of smoke inhalation contributing to rapid animal deaths. This pervasive layer also blocks sunlight, compounding environmental stress by reducing temperature regulation and photosynthesis in plants. Large sauropods trample through burning undergrowth, their massive forms both fleeing the advancing flames and inadvertently reshaping the landscape. Herd behavior drives a chaotic stampede, uprooting smaller plants and compressing the soil, while younger or weaker individuals fall prey to the conflagration. Trackway fossils from late Cretaceous deposits suggest sudden, wide-ranging movement consistent with panic-driven herding, giving insight into the behavioral response of massive herbivores facing imminent danger. Scorched soil and fallen embers create treacherous terrain for fleeing herds. The combination of intense heat and unstable ground forces stampeding dinosaurs into narrow channels and gullies, where many become trapped or injured. Fossil trackways suggest sudden deviations in herd paths, indicating panic and confusion. Smaller herbivores, including ceratopsians and hadrosaurs, are particularly vulnerable. Their skeletal remains found near toppled trees and scorched underbrush. Fire not only directly harms creatures, but also reshapes the landscape in real time, influencing survival chances through obstacles and hazards created by the inferno itself. Thermal radiation from re-entering ejecta ignites tinder-dry vegetation ahead of the advancing fire front. Grasses and conifers, particularly resin-rich species, burst into flame spontaneously as temperatures spike. Fire spread modelling suggests that these spot ignitions could leap tens of kilometres in minutes, creating isolated infernos that merge into continuous walls of fire. Evidence of heat-induced fractures in fossilised trees confirms the intensity of thermal exposure in proximal zones. Small mammals scurry into burrows, but smoke infiltrates even subterranean refuges. Fossilised remains of early marsupials and multituberculates show carbonised deposits within skeletal cavities, indicating that even creatures seeking shelter were not fully protected. Behavioural adaptations, such as burrowing or clustering, fail to counteract suffocating air, demonstrating that survival depended on chance location as much as instinct. Flying reptiles and early birds attempt desperate escapes, wings beating against acrid air. Pterosaur fossils preserved near the KPG boundary suggest individuals died mid-flight, while feathered dinosaurs struggle to navigate dense smoke and falling embers. The aerodynamic challenge is compounded by heat stress, with rising air currents pushing some creatures beyond safe altitudes and others into the advancing inferno. Smoke-filled skies distort navigation, disorienting even the most agile flyers. Ash and dense particulate matter obscure landmarks, while thermal currents buffet flying reptiles and birds. Fossil evidence suggests many pterosaurs perished at altitudes far from their nesting grounds, unable to maintain flight or avoid collapsing thermal pockets. Some birds attempted to descend into rivers or lakes for respite, only to find the water surface scalding from floating embers. These combined stressors, heat, smoke, and erratic air currents, demonstrate that the aerial escape routes that might have offered hope were themselves fraught with lethal challenges. Charcoalized layers in fossil beds reveal the staggering speed and intensity of these wildfires. Analysis of paleosols shows that some areas experienced repeated burns within a single day, evidence that firestorms could sweep across entire regions multiple times in rapid succession. This repeated exposure amplified mortality and destroyed potential food sources, leaving survivors facing both immediate heat and longer-term starvation. Embers carried by the wind ignite distant patches of forest, creating isolated infernos across the continent. These secondary fires, appearing hours after the initial ignition, trap species attempting to return to safer zones. Fossilized leaf litter and ash layers indicate that fire fragmentation patterns created microhabitats of death and survival, foreshadowing how scattered refuges would shape post-impact recovery. Evidence of heat-induced bone fractures in fossils indicates direct thermal stress on some larger animals. Vertebrae, limb bones, and skulls of dinosaurs and large reptiles display warping and microfractures consistent with rapid exposure to extreme surface temperatures. Combined with inhalation of smoke and loss of shelter, these injuries illustrate that fire was not only a predator of convenience, but a mechanistic killer capable of immediate physical trauma. In sheltered valleys and shaded hollows, only a few hardy species survive, clinging to the fragile promise of continuity. Some small mammals and reptiles emerge from burrows once flames pass, finding ash-coated vegetation and partially scorched waters. Fossil evidence of survival clusters suggests that only species with rapid reproductive cycles, burrowing behavior, or mobility could endure this planetary inferno. These pockets of resilience hint at the uneven and precarious path to post-impact recovery, while the broader landscape remains a tableau of smouldering ruin. The planet, ablaze in fire and smoke, mirrors the silent depths of the oceans before it, showing that both land and sea are swept by cataclysm in tandem. Flames may subside in isolated refuges, but the legacy of heat, ash, and chemical disruption ensures that life will face yet more obstacles in the hours, days, and months to come. From these smouldering landscapes, only the hardiest creatures cling to survival, preparing the stage for the next chapter of planetary upheaval. Skies choked with soot, sulfur, and a poisoned atmosphere that challenges every breath. Echoes of survival. Emerging cautiously from charred burrows, small mammals probe the ash-strewn landscape. The ground is still warm, and lingering smoke makes the air heavy, but instinct drives these creatures to search for food and water. Fossil evidence of early marsupials and multituberculates shows that burrow networks insulated them from the extreme heat and provided shelter from predators. Their diets shift to roots, seeds, and detritus, exploiting resources overlooked by larger herbivores now decimated by the fires, illustrating the importance of flexibility for survival. Below the scorched soil, reptiles lie in suspended animation, their metabolism slowed in subterranean sanctuaries. Fossils indicate small lizards and snakes could withstand hours of extreme heat above ground by retreating deep into tunnels or crevices. Burrow depths of 30-50 centimeters buffered against lethal temperatures and smoke, showing that even modest shelters could mean the difference between life and death. These refuges allowed a subset of terrestrial fauna to persist, forming the foundation for post-catastrophe recovery. Deep in the oceans, plankton and nekton ride thermally stable currents far from surface turmoil. Stratified layers prevented extreme heat pulses from penetrating the mesopelagic zone, allowing photosynthetic microorganisms and small invertebrates to survive. Fossil evidence from foraminifera and coccolithophores indicates that these populations persisted despite catastrophic surface changes, providing the nutritional base for higher trophic levels once ecosystems began to recover. Apex predators, including large fish and mosasaurs, faced starvation but could intermittently exploit these stable zones to sustain fragile populations. Ash-laden rivers deliver nutrients to pockets where aquatic plants endure, their roots anchoring them against scouring currents. Fossilized remains suggest that freshwater refuges, riverine pools, floodplain depressions, and oxbow lakes provided microhabitats for fish, amphibians, and invertebrates. Sedimentary layers rich in charcoal and organic matter highlight the dual nature of fire, destruction paired with enrichment, creating microenvironments capable of sustaining isolated populations. Rocky outcrops and collapsed caves become critical shelters for insects, amphibians, and early mammals. These microhabitats preserve moisture, moderate temperature, and block embers, providing temporary lifelines amid scorched landscapes. Fossilized remains of arthropods and amphibians suggest that species persisted in these isolated refuges, their populations fragmented but viable, revealing the mosaic of survival that would shape later recolonization. Fossilized burrows and shell beds record the persistence of life amid chaos, leaving evidence of resilience for millions of years. Complex tunnel networks indicate repeated use by small mammals, while bivalve shell beds reflect survival in aquatic refuges despite nearby mass mortality. These geological records demonstrate how localized environmental stability could preserve species when global systems were in collapse. Some plants sprout from seeds insulated beneath ash layers, timing germination to environmental cues once the heat subsides. Ferns, cycads, and early angiosperms survive through dormant seeds or vegetative sprouting, providing the first green shoots in a desolate landscape. Paleobotanical studies reveal that these early pioneers not only restore habitats, but supply critical nutrition for recovering herbivore populations, illustrating the interconnectedness of survival across species. Isolated lagoons and sinkholes act as lifeboats for turtles, amphibians, and micromollusks. Fossil evidence indicates that temperature stability, partial shading, and nutrient availability created microclimates capable of sustaining life while surrounding areas burned. These pockets highlight how topography and water availability could dictate survival, emphasizing that life persisted wherever local conditions allowed, even briefly. In shaded canopies and fractured rock ledges, small birds and arboreal reptiles find temporary sanctuaries from the lingering heat. These microhabitats allowed early feathered dinosaurs and small arboreal reptiles to survive by exploiting vertical space, avoiding ground-level fires and predators. Fossilized perches and claw marks in petrified wood suggest repeated use of these refuges. Some species likely shifted diets toward insects, emerging from charred vegetation or the seeds of pioneer plants sprouting post-fire. This vertical refuge strategy demonstrates how spatial flexibility and microhabitat selection could dictate survival, adding another layer to the mosaic of persistence across ecosystems. Behavioral adaptations, such as nocturnal activity and deep burrowing, help some animals avoid heat and predation simultaneously. Fossil analysis shows that mammals' reduced size, specialized burrow construction, and altered activity patterns to cope with extreme environmental stress. These adaptations, combined with physiological flexibility, underscore the role of behavior in determining which species would endure and ultimately repopulate devastated regions. Predator-prey interactions continue even amid devastation, with survivors exploiting weakened or trapped individuals. Fossils suggest small carnivorous mammals and reptiles scavenged carcasses of burned herbivores, while amphibians preyed on insects drawn to charred vegetation. These interactions highlight that ecological processes, though muted, persisted in microhabitats, driving selection pressures even under extreme stress. Even underground chemical stressors such as smoke infiltration, ash-laden water, and temperature flux shape survival. Burrow depth, orientation, and ventilation become critical variables, and fossils reveal signs of repeated use and occasional mortality within these shelters. Life persisted not because conditions were ideal, but because these microhabitats provided partial protection from the worst environmental extremes. Flowing unseen beneath the scorched earth, even subterranean waterways and hidden aquifers become critical lifelines, sustaining species when surface conditions are lethal. Fossilized mollusks and small fish found in protected springs indicate that freshwater refuges buffered against heat and ash fallout. These aquatic microhabitats provided oxygen-rich water and moderated temperatures, allowing isolated populations to persist while surrounding rivers and lakes were devastated. Isotopic analysis of shell material reveals that these pockets remained habitable for weeks after the fires, serving as crucial genetic reservoirs for species repopulating aquatic ecosystems. This underscores the importance of hydrogeological refuges in preserving biodiversity during global-scale catastrophes. From these scattered refuges, life begins to prepare for a slow expansion, seeding the genetic diversity required for ecosystem renewal. Small mammals, burrowing reptiles, deep-sea plankton, and resilient plants collectively form the blueprint for recovery, representing the thin but vital line connecting extinction to future evolution. Fossil records and sediment analyses suggest that these survivors would repopulate niches cleared by catastrophe, illustrating the enduring tenacity of life and setting the stage for evolutionary innovation. The echoes of survival, though fragile, resonate across the scorched planet, showing that even amid catastrophic fire and ash, pockets of life endure. These resilient survivors hint at the evolutionary transformations that will follow, bridging the gap between planetary devastation and renewal. From the darkness of underground burrows, the depths of oceans, and the shelter of isolated microhabitats, life's persistence demonstrates an unyielding drive to endure, adapt, and, ultimately, flourish in the new world emerging from fire and ruin. The world reborn in ash. Amid a sky heavy with ash, the first tentative shoots of pioneer plants pierce the scorched soil. Ferns, cycads, and early angiosperms exploit seeds insulated beneath layers of fire-scorched earth, germinating only when temperatures fall to tolerable levels. Paleobotanical evidence shows that some species could sprout within hours to days, supplying the first green shoots in a landscape otherwise bereft of life. These early colonizers provide crucial nutrition for surviving herbivores and act as stabilizers for the soil, preventing erosion as rain begins to fall on the desolate terrain. The resilience of these plants demonstrates that even in the aftermath of global devastation, life's persistence hinges on rapid adaptation and strategic use of environmental niches. Rivers, once choked with fire debris, begin to carry diluted nutrients, creating pockets of habitability for freshwater life. Fossilized remains of small fish, amphibians, and mollusks indicate that microhabitats along river bends and oxbow lakes acted as refuges, sheltering aquatic organisms from both thermal spikes and suspended ash. Nutrient influxes from burned vegetation enrich the water, allowing plankton and benthic invertebrates to proliferate, forming the foundation for food webs that survived the initial catastrophe. Chemical analyses of sedimentary layers show higher concentrations of organic carbon and trace minerals, revealing how destructive events paradoxically create localized fertility. In these microcosms, early ecological succession begins, a fragile spark of recovery in an otherwise hostile world. Movements of survivors ripple cautiously across devastated landscapes, their behaviors shaped by both opportunity and danger. Small mammals, including early marsupials and multituberculates, venture from burrows, exploiting charred seeds, roots, and detritus left in the wake of fire. Reptiles and amphibians emerge from crevices and collapsed rock shelters, timing activity with brief reductions in surface temperatures. Fossil trackways demonstrate selective foraging patterns, showing that survivors actively avoided areas of lingering heat or toxic ash deposits. These movements, measured and deliberate, illustrate how behavioral flexibility and spatial awareness were critical determinants of immediate post-impact survival. Microclimates hidden within fallen logs and beneath rock overhangs offer temporary shelters for insects and small reptiles. These pockets maintain slightly higher humidity and cooler temperatures, buffering against extreme surface heat and ash-laden winds. Fossilized remains of beetles, scorpions, and small lizards suggest that such microhabitats allowed species to survive initial post-impact days. Observations of burrow proximity indicate that these temporary shelters were often connected to longer-term refuges, creating small survival networks. These refuges highlight the importance of structural heterogeneity in terrestrial ecosystems for early post-catastrophe persistence. Fossilized footprints in ash layers reveal the movements of small mammals and reptiles navigating the new terrain. The patterns captured in sedimentary deposits indicate repeated use of safe corridors connecting burrows, shaded ledges, and nearby water sources. Some prints intersect, suggesting early predator-prey interactions as carnivorous species scavenged weakened or trapped individuals. These traces underscore the persistence of ecological dynamics, even amid widespread devastation, and provide paleontologists with a vivid snapshot of life on the first day after the impact. In isolated coastal lagoons, marine life persists, buffered from the worst thermal and chemical effects. Stratified water layers protect plankton, mollusks, and juvenile fish from extreme surface heat and acidification. Fossil evidence from bivalve beds and microfossils demonstrates survival in these localized refuges, suggesting that even large-scale oceanic disturbances leave patches of habitability. Apex predators, including mosasaurs and large teleosts, face food scarcity but can exploit these refuges sporadically, maintaining fragile populations. These coastal sanctuaries highlight the uneven but essential pathways by which marine ecosystems begin to stabilize. Volcanic-like plumes of dust and sulfur continue to alter atmospheric chemistry, influencing early plant regrowth and animal activity. Aerosols reduce sunlight, creating cooler microclimates beneath canopies and over water, while simultaneously lowering photosynthetic rates for exposed species. Geochemical analyses of sulfur-rich sediments confirm widespread deposition, demonstrating how atmospheric perturbations controlled both plant germination and animal foraging. This complex interplay between chemistry and ecology underscores the fragility of life's recovery and the subtle environmental cues that guide it. Charred tree canopies act as nutrient reservoirs, slowly releasing minerals as they decompose into the ash-laden soil. This process enriches pockets of ground with calcium, potassium, and trace metals, supporting early plant regrowth and soil microbial activity. Palynological evidence indicates that ferns and cycads preferentially colonized these enriched zones, creating the first patches of biomass capable of supporting herbivorous survivors. Meanwhile, decaying wood and fallen branches provide shelter for invertebrates and small mammals, forming micro-ecosystems that foster predator-prey interactions despite widespread devastation. Such localized nutrient hotspots accelerate ecosystem recovery, demonstrating that even destroyed forests continue to contribute to life's resilience. Soil analyses show early post-catastrophe enrichment, with charcoal layers supplying nutrients for emerging flora. Sediment cores reveal concentrations of nitrogen, phosphorus, and trace metals derived from burned vegetation, creating patches of fertile ground amid desolation. Pioneer plants exploit these nutrient hotspots rapidly, their roots stabilizing ash-laden soils and fostering microbial communities that enhance further growth. These processes illustrate the dual nature of catastrophe. While destruction dominates, it simultaneously sets the stage for renewal, demonstrating the intricate connections between geology, chemistry, and biology. Interactions between surviving predators and prey resume cautiously, demonstrating the earliest steps of ecological reconstruction. Small carnivorous mammals and reptiles capitalize on weakened herbivores, while amphibians and insectivores exploit proliferating insects drawn to burnt vegetation. Fossil evidence suggests these predation events were highly localized, limited to microhabitats where food was accessible. Even in fragmented ecosystems, natural selection continues to operate, shaping species that endure and pass on traits essential for post-catastrophe resilience. Patches of refuges form a mosaic of life, indicating the uneven but persistent recovery potential of ecosystems. Across mountains, valleys, coastal lagoons, and subterranean shelters, species exploit specific niches to survive, creating a patchwork of surviving populations. Fossil records indicate repeated burrow usage, persistent shell beds, and isolated plant growth, revealing how survival depended not only on individual adaptability, but also on the availability of protective microenvironments. This mosaic underscores the contingency of life. Where conditions allow, even the smallest pocket of stability can sustain entire lineages. Within these fragile pockets, evolution's blueprint for renewal quietly begins, hinting at the mammals and new species that will dominate the post-impact world. Fossil evidence shows that small mammals and reptiles reproduce rapidly in these refuges, maintaining genetic diversity despite harsh conditions. Microbial and plant communities begin recolonizing soils, supporting herbivores that venture from shelters. These early dynamics set the stage for post-catastrophe ecological networks, ultimately leading to the rise of mammals, birds, and new ecosystems that would define the Cenozoic era. The first day concludes with a planet irrevocably altered, yet life's tenacity ensures that recovery, however slow and uneven, is already underway, bridging destruction and the promise of renewal. The sky fades from fire to ash, and in the silence that follows, Earth bears the scars of a single, unstoppable moment. Life, fragile yet tenacious, clings to hidden refuges, whispering of survival amid unimaginable loss. We witness both the fragility of existence and the quiet persistence that allows the world to begin anew. As shadows lengthen over a transformed planet, the echoes of that fateful day linger, reminding us of the delicate thread that connects all life. If this journey stirred your wonder, explore more by subscribing and sharing your thoughts below.